ladies and gentlemen, we have a task today. Put the track up on one book and put the two cylinders near the top and let go of them at the same time.
Now, we wish that you were here, so here's the track. Set up on one book, and there are two cylinders. The trick is releasing them so they don't.
Touch
All right.
the side. 1, 2, 3.
One was fast, one was slow. Which was which?
Fast and slow. Fast and slow. And our question is, why don't they reach the bottom at the same time? Why not? Should we do it again?
Sure, why the hell not? So I noticed that the slow one's got a piece of tape on it. Let's see if it is slow again the second time. So let's take your mark.
Whoa, whoa, whoa. Okay, mark, get set.
Yep,
Slow.
the one with the tape was slow both times.
So why don't they reach the bottom at the same time?
That's a good question.
Let's go ahead and open these guys. So this one was the fast one. And lo and behold.
Isn't that interesting?
And now for the slow one. You know what's funny is I can always tell like when I record videos based on my nail color. Okay. So and here we go. So what's different about these?
All right. Well, the black part is the same. You have a central axis that's the same, and you've got ball bearings, steel ball bearings that are in different places.
So the fast one was closer in, and the slower one was further out.
Okay, what are they supposed to do?
Okay, good question. Okay, your task. I want you to pause the video here.
One more.
Oh, not this one. Yeah. And develop an explanation for the difference in the accelerations. Go ahead.
Go ahead. Go ahead.
Okay, why was there a difference in accelerations?
So pause this, scratch your head, and see if you can write down something that might explain why this one was fast and this one was slow. Go!
Okay. So, now that you've done that, let's go and talk some more. Inertia is an object's resistance to change in its motion. Mass is a measure of inertia.
We know that already. Yeah.
More mass, more inertia.
Yeah.
In translational motion, all particles move parallel. So that inertia is proportional only to the mass. More mass, more inertia.
That's right. Why you will kick the soccer ball but not the bowling ball.
Don't do it.
Don't do it.
In rotational motion, all particles follow circular paths around a central axis, so that rotational inertia depends on how far the mass is from the center.
Well, I think we've got an example of that.
So we were experiencing rotational inertia here. We have a mass that's closer to the center here, and it went faster to the center of the rotational axis, and over here, further away.
Oh. So what's the relation? Hold on. What's the relationship? Because we've got the same masses here, so how far means more rotational inertia or less rotational inertia?
So how far means more rotation. So the further it is, the more rotational inertia it's going to have.
Yeah.
Because it went slower.
Yep.
Right? Resistance to change in motion.
We saw that.
The closer in it is, the less rotational inertia it has.
That was the fast one.
That was the faster one.
Cool.
Good point. I'm glad you pointed that out so I can say it. Okay. The moment of inertia that resists rotation is determined by the distribution of mass inside the object.
This is a new idea. This is an important idea. Moment of inertia. It's a bunch of words symbolized by the capital letter IE.
IE. And this is inertia, the moment of inertia, but for rotational motion. And instead of just being directly proportional to the mass, it is related to the distribution of the mass.
Yeah.
Hold a long object in the center and twist it.
So do you
Now,
guys have a ruler or a hammer or
ruler.
something like that?
Something, okay?
We have a meter stick here.
Okay, or so I'm not hitting. So hold a long object in the center and twist it.
She's getting all kung fu up in here.
Okay, now hold it on the end and twist it. Feel, ow, my hand.
Don't go up and down, just twist.
Oh, twist like this?
Yeah, there you go.
Okay.
Now see how
Feel the
slow she can do
difference.
that? She's a pretty strong person, but that's slower than when you hold it in the middle. Now, if you're doing this at home, you should be able to feel it too.
How is that like this?
That's a good question.
Right, the mass was further apart, and the masses were further apart from the center of the axis of rotation. They went slower.
Yeah.
Again, my hand is not in the middle; it's further
So her
apart.
hand is the axis of rotation,
Okay, going slow.
and so you got a bunch of mass that's farther away. When you hold in the center, what's different?
Okay, when I'm holding the center, the mass is
Closer to your hand.
Yeah, it's closer to the axis of rotation, just like these ones were, and we went faster.
If you were here, everybody have a meter stick. You could do this yourself. You could feel the difference for your own bad self.
Everybody will be kung fu fighting. Okay. How could we rewrite Newton's second law to apply angular motion?
Okay, so Newton's second law of motion is pretty important. The question arises, here it is for translational. What are the analogous ideas for rotation?
Well, we know that the torque net is equal to force times the lever arm. And so this and this are analogous. Get my paper here. See what the next slide is.
So
We just kept- oh, yeah,
where
next
we
slide.
have net force, so underneath the second law over there on the left, write down torque net.
Wait,
On
say it
the-
again. Oh, over here.
Yeah.
Oh,
So torque net.
I'm gonna go like this.
Don't write anything after
Oh,
it.
not yet.
You've already got that.
I know. I was like, wait, what do I do?
So what's analogous to mass for things going around a circle? I think we just found that out.
That's inertia, right?
Moment of inertia.
The moment of inertia. And then for rotational, this is linear. For rotational, what about for acceleration?
What's that symbol for angular acceleration? That's it. So there we've got it. There's Newton's second law applying to angular motion. What's the next slide?
Next, there it is. Torque, the moment of inertia times the angular acceleration.
And that's Newton's second law. So it applies to translational motion.
And also
Yeah.
rotational.
You just have to change the players, but the idea is the same.
And what are the units of torque and acceleration? Okay, so the units for torque.
You've got it up there on the right already.
Okay.
You've got it up there on the right
torque
already.
up here, Newton meters. So that's going to be a Newton meter.
Yeah, Newton times meters.
And then acceleration.
Angular acceleration.
Where should I write that? Forget where we're going to write it at.
You can put it right under
Right
torque
underneath
net.
it? Right here?
Yeah.
It's going to be radians per second squared.
Yeah.
Okay, what's next?
Solve that equation for I.
Okay, so I'm going to go ahead and just say I equals torque net divided by acceleration. What are the units for I? Oh, okay.
You just take the units that you've already got.
Newton meter divided by radians per second
Now,
squared.
funny thing about radians, they disappear in
They just
unit.
go
They
away.
appear and disappear as appropriate.
I'm going to go ahead and just flip this, you know?
Yeah.
So squared, and then I'm just going to ditch the radians, right?
Yeah. So when you divide by a fraction,
Yeah.
you flip it over,
But I'm just going to get rid of that.
and so that gives Newton meters second squared.
Okay.
What is a Newton though?
Well, Newton is
Comes
mass
from
times
Newton's second law.
acceleration. So kilograms times meters per second squared time meter second squared. These cancel.
And you got meters times meters.
That's going to be meters squared.
So the units of moment of inertia are kilograms meters squared.
Okay. Kilogram squared. Kilogram squared. Okay. And I. The moment of inertia, I, varies with mass and distance. from axis of rotation.
Yeah, that's what we've been talking about. We got some pipes over here.
Okay. So we have a pipe and two clamps, a pipe and two clamps.
They both have the same mass. The clamps have the same mass, pipes, so the weight of both of these, the mass of both of these are the same.
So what was I gonna do? I was gonna go like this.
You're
right?
gonna twist it in the middle.
Okay, I'm twisting in the middle. Notice how fast I'm going.
Okay, all that mass is out on the ends. That's a larger R radius. And
Okay.
here, how fast can you make this go? Oh, check it out. Much
Fast,
faster.
right?
Yeah.
That was easy.
And
Easier.
the reason is the distance from the axis of rotation is small here, and the distance from the axis of rotation is large
And
there.
which one has a greater moment of inertia? Well, which one's harder to move?
That's right,
This one.
the big one.
Okay, and again, how is that like this? It's the same as this. Okay.
Oh yeah, that's with the clamps out on the ends. This is like the clamps in the middle. You can't make this go as fast because there's more resistance to angular motion.
My next thing says page 232. Okay, so page 232, and we have table 9.1, moments of inertia I for various rigid objects of mass m. So we have a hollow cylinder here, we have a solid cylinder here.
And let's just take a look at the moments of inertia. That's mr squared.
mr squared, and this one is 1/2 mr squared. Why is it 1/2?
We just happen to have,
Two cylinders, one hollow, one solid.
they have the same mass,
Same mass, and
the same radius.
yes, and they have the same radius. But this one's moment of inertia is represented by mr squared, and this one's 1/2 mr squared.
So let's roll them down the ramp.
So actually, let's make a prediction, you guys. Before I go,
I like that.
which one do you think is going to be faster?
Which one will win the race, assuming that it doesn't rub against the side of the track?
Let's see if I can do that here. Okay, ready?
Yep.
Set, go.
Oh, snap!
Smoked it.
Oh, snap!
Woo! Okay.
It's almost as if it was going twice as fast
Okay.
as the other. No, that's good.
That's good?
That's because
That
if
was
you
a
run
good
it again,
trial.
that was a good trial. We'll live with it.
So what's going on here? Well, first of all, the question is which one? So which one won? The solid one won,
Yeah.
right? And why is that? Well, if you look at the moment of inertia for the solid block,
Yeah.
it's going to be half as much.
Yep.
It's going to have a smaller moment of inertia.
Less resistance to change in its angular motion.
And this one will have a greater moment of inertia, which means it more so doesn't want to change what it's doing.
Yeah, that
Right? It wants to stay sitting there.
That goes back to this. It's the ring has got all the mass around the edge, like the slow one. And this one has all the mass evenly distributed, which is not exactly the same as this, but closer to
Put
it.
closer to that.
Yeah.
Okay. Oh, actually, you know what? Our next slide is still in the
Now,
book.
I'm going to just,
Oh, yeah. Want me to go back there?
well, what we've got here is we have a bunch of different, and you can open your book and look at the difference. And what's the same each time is mr squared, mr squared, mr squared, mr squared, ml squared. Okay, but the only thing that's different is the fraction
In
in
front.
front of each. Now, you won't have to memorize. The only one you'll have to memorize is the first one.
MR squared. All right. You ready?
It's that time of year, isn't it?
Okay, example 9. Inertia equals mr squared. What does this mean?
That's the Greek letter sigma, isn't it? And it means sum.
The sum of, so the moment of inertia for a particle, that's what we're talking about here, is going to be the sum of the mass and their radius squared. So let's take a look at this question.
So grab your books, boys and girls, and read along with us on page 232. Go ahead.
Example 9. Two particles each have a mass m and are fixed to the ends of a thin, rigid rod, whose mass can be ignored. The length of the rod is L. Find the moment of inertia when this object rotates relative to an axis that is perpendicular to the rod at A, one end, and B, the center.
Could you demonstrate that with a meter stick? Where'd our meter stick go? That's over there. Now, what we're going to do is we're not going to work this out. We're just going to read what the book has because that's good practice. Okay.
Point here,
All
right? And we're rotating around a center of axis and with a length of L, and the
Yeah.
L is the length of this.
Yeah.
And it's just rotating.
So on
rotating
this
like
one of the masses is at the center of rotation, and the other mass is L away. And then when you hold it in the middle, what do you got?
right here. So now one of the particles is here and the other one is right here.
No, the
halfway
other
in.
one's on the end. It's still on the end. Your axis of rotation's in the center.
Oh, sorry, right here.
So and then you spin it. All right, so how does the book explain the answer to this?
Okay, so what the book says is, so particle one, well, should I just talk about the words?
Well,
the
let's
math here?
do the reasoning first.
Okay.
Let's go.
When the axis of rotation changes, the distance r between the axis and each particle changes. That makes sense.
Yep.
Right? In determining the amount of inertia used, I equals the summation of mr squared.
Add them all together.
Yeah, we must be careful to use the distances that apply for each axis. So what's changing? This versus this.
Right.
Solution one, particle one lies on the axis as part A of the drawing shows and has zero radical distance, r1 equals 0. That just means it's right there.
Here's a drawing down here.
Oh, look at that. Okay. R1 equals 0.
R1 is going to be equal to L. Oh, R1 is 0. That's because the distance to the mass is at the axis.
Yeah, it's at the axis. In contrast, particle 2 moves in a circle whose radius is L. So, this.
Yep.
Okay. Or a longer distance
Yep.
here. Or this one right here.
Well,
no,
we're still
A.
working with the first one.
Hey, I like my better.
I do too.
Noting that m1 equals m2, the masses are the same, we find the moment of inertia is, well, we know the equation is mr squared, and we just have, and we have two particles, so we're going to do the mass one, the first particle in that radius, plus the second particle in that radius.
And that
squared.
first particle, the radius is 0, so that drops out.
And the second one, it is?
L squared, since L is the radius.
Yeah, and so we get this final equation right here.
Okay, now when you go to the other one.
For part B, part B, the drawing shows that particle 1 no longer lies on the axis but moves on a circle of radius r1.
So that's this right here.
Yeah. So it's going to be moving halfway in there.
Yeah.
So R1 now has a radius of L2. Particle
L divided by
L
2.
divided by 2. Sorry, excuse me. That's important. Particle 2 moves on a circle with the same radius. So radius 2 is also
So
L2.
they both have the same radius. They both have the same mass. And so when you go to the math here in the next line,
You've got the mass and the radius plus the mass and radius squared. But what does that look like? Well, our radius is really L over 2, and then this one is L over 2 as well.
so when you square L over 2, you square the L, you square the 2, you end up with L squared over 4
Plus
1/4 plus 1/4.
And that gets you a 1/2.
1/2.
Yeah. And if you're having trouble visualizing that letter B, instead of one particle being here and one being here and it rotating, it just means that this particle now comes in here.
No.
No?
The particles stay in the same spot. The only thing that's changing is the axis of rotation.
Gotcha. So rotating. That's a great point.
Yeah.
So I'm rotating like this around the axis. My axis is at, this way, 50. You
Yeah.
can see it right there.
Yeah.
Versus before it was like this.
Yes.
Oh, I totally get that.
All right.
Okay, let's do it.
It's like everything that we've been seeing so far.
Bada boom. Okay. Did we cover everything we needed to there? Was that good? Yeah.
Well,
yeah.
That's everything. You
Yeah.
can go back to that problem. It went away.
Okay. Ladies and gentlemen, go ahead and take a stab at this.
An electric saw brings a blade from rest up to 503 radians per second in 6 seconds. What net torque must the motor apply to the blade if the moment of inertia is 0.00141 kilograms meters squared? Okay, so from rest, what does that mean?
That means and we're talking about angular here, so
Yeah.
our angular velocity is going to be 0 meters per second.
And 503 radians per second must be,
503 radians per second, my final angular velocity.
and 6 seconds is time.
Time equals 6 seconds. And what are we trying to find here?
The net torque. Well, that's Newton's second law. That equals I alpha.
Wait.
Yeah.
Oh, yeah, sorry. Equals times acceleration, right?
Yeah. Okay, so let's do the acceleration first.
Oh, and we also have the I here.
Oh, yeah, they give us I.
0, 0, 1, 1, 4, 1.
Kilograms meters squared, yeah.
Meters squared. Okay. And if you're like, Miss Moore, how'd you get this? This is just force equals mass times acceleration.
Yep.
Okay, so we have this, we're missing this, we need this. So let's go ahead and find acceleration. Using our kinematic equations, we know that acceleration is this. Let's go ahead and find that. So 503 radians per second minus
0.
0. Oh, did I say 0?
It should be 0.
I said meters.
Ah!
Radians per second. Divided by 6 seconds.
503 divided by 6.
503 divided by 6. Okay, 503 divided by 6. That's going to be 83.8 radians per second squared. 83.8 radians per second squared.
So now we know the angular acceleration. We've got the moment of inertia. Now it's plug-in time.
0.00141 kilograms meters squared times 83.8 radians per second squared. Bada boom. So that's gonna equal, that's a lot of numbers. Okay, 0.00141 times 0.838, and I didn't do that right. 0.00141 times 83.8, right?
Yeah.
And I get 0.118.
0.118. And the units of torque are Newton meters. Boys and girls, on your own, can you justify how we get Newton meters out of those units right there? Do that on your own. Remember, radians go away.
Mm-hmm. Radians disappear. I see it. Okay.
And now you don't see it.
All right, and homework time. So for homework today, you're going to do page 246, number 32, 34, and number 36.
Sweet.